Hey guys, welcome to the second episode of Technical Tuesdays. This week we're going to be focusing on the inductor. Since I don't have an oscilloscope, we're basically going to focus on the concepts and finish out the episodes with non-ideal behaviors of the inductor. So we're going to begin with the basic concepts of the inductor. Well, exactly what is it? An inductor is a passive two-terminal electrical component. Its main job is to resist changes in electrical current. It stores its energy in a magnetic field, and it's designed by having a long conductive wire that's coated enamel that's usually wrapped in a coil. So the electronic or schematic symbol, which is just a visual representation, is similar to the resistor, but it varies because it's just a line and humps and a line's finisher, which shows that it's two terminals. Its units is henries, which is denoted by the capital H, and inductance is just a L, a capital L. And really what inductance is magnetic flux over current. And the impedance of the inductor is Z, which is impedance equals J omega L, with omega equals 2 pi of the frequency it's operating at. So now we're going to talk about the series and parallel combinations of inductors. When inductors are hooked up in series, or when the current only has one path, the equivalent inductance is 1 over equivalent inductance equals 1 over L1 plus 1 over L2 plus 1 over L3, and it just goes on forever. In parallel, or when current has multiple paths, the equivalent inductance is just a summation of all the inductances. It's opposite of resistors. So we're going to talk about a few of the principal equations for the inductors. We're first going to begin by talking about Faraday's law, which describes the voltage induced by the inductor, and it's V equals L di dt. So it's basically saying the voltage equals the inductance times the time rate of change of the current, and that gives you the voltage, and the of T is at a certain time, because inductors work with time varying currents or AC signals. Then Lenz's law. This is what describes what I was talking about in the beginning of the video, where the inductors, one of its main jobs is to oppose changes in current. Lenz's law works off the principle off of the right hand rule. So I'm just going to begin by drawing, just pretty much treat that as a wire. And if you have current flowing this way, we take our right hand, have your thumb point in the direction of the current, and just curl your hand. And that tells you the way the flux is curling. So with the current going up, the flux is going to wrap around this way. So I'm going to draw these. So when the current changes directions, now we gotta flip our hand down so our thumb points in the way of the current and wrap our hands that way. So the flux would be wrapping that way. And as I described, inductors store its energy in a magnetic field. So when the current flows this way, it's storing this energy through this motion of a magnetic field. And when the current changes directions, these two fluxes are going to hit each other, and that's how it opposes its changing current. You can actually make inductors at home. We're going to use this equation right here to make an open air circular inductor. So what you're going to want to first do is take a long wire that's enamel coated. For this instance, I'm going to use this long wire that's insulated. So you're going to want to take something circular. I'm going to use this Phillips head screwdriver. And what you do is wrap the coils tightly and together like this. So that's basically an inductor. So let's just talk about this equation right here. It's inductance equals R squared N squared divided by 9 times R plus 10 times L, with R equals the outer radius, and we use imperial units for this, so it's going to be in inches. The lowercase l being length, uppercase L being the inductance you desire, and the uppercase N being the number of turns. So with this equations, you can actually design and build your own inductor for a specific value. Inductors have a lot of use in today's world. We're going to first begin by talking about transformers. Basically, a transformer is two inductors with a ferrite material and laminations and all that, but we're going to stick to a high-level view of it. So a transformer has one inductor that's the primary side and another inductor that's the secondary side. When you put an AC signal through the primary side, and that creates magnetic flux which gets coupled into the secondary side, which induces a voltage across the secondary side. So for this, we use this equation right here. The voltage primary over the voltage secondary equals the number of turns primary to the number of turns secondary. So let's just do a quick little example. Say we have 120 volts here, 10 turns here, 1 turn on the secondary side. We could actually find out what the induced voltage is going to be on the secondary side. So using this equation, we should see that 120 over the secondary voltage, because that's an unknown right now, should equal 10 primary turns over 1 secondary turn. So if we, multiply and divide, we see that the secondary voltage should equal 12 volts. So that's how inductors are used in transformers, but they're used extensively through filter design. So we're going to begin by a basic filter, which is just putting an inductor in. Well, we're going to first begin by putting an inductor in series with a load. And inductors for, say, a DC signal, they're just considered shorts. It's just another piece of wire that's just going to allow the current to go through. So when the inductors are placed in series, it blocks out the AC signal, because as we described earlier, inductors like to resist change in current. When inductors are in parallel, it allows the DC signal to go to ground and allows the AC signal to pass. If you put an inductor in parallel with the capacitor, you get what is called a resonator. With this equation we saw last week that the omega naught equals 1 over square root of LC. And this creates an AC signal to resonate at a certain frequency. You usually design this to resonate a frequency that you don't want for basically an EMC standpoint, or if you're picking up unwanted noises in a circuit, you put this in series with whatever it is to take out that noise. There's also these two uses for inductors, which are common mode chokes and differential mode chokes. This is just a little above what we should get into today, but it's basically that if you put two alternating currents through here, they cancel out, and the differential mode too. This is just a little above what I want to get to, but this is just another example. There's also extensively more. You can see if you take any switched power supply, and if you look at here, this is just a ferrite bead choke on here. Now we're going to move on to my favorite portion of this. We get into the non-ideal behaviors of lump components. So basically, to start off with, an inductor seems fairly simple, but its equivalent model can get really complex. So from this model, we're going to depict the equivalent model for it. So we're going to first begin by, well, as we described in the resistors one, we do get some inductance from the leads. So we're going to add, I guess we'll just put that, it goes here, and then we'll add an inductance from the lead. So then we also are going to get a capacitance effect from these two, where the current going in here is going to cause displacement current at this lead. So we should see a capacitance effect in parallel with this. We'll move on. Then we should reach just the normal inductance of the inductor. But then we also know that even copper or anything is not purely conductive. There's always going to be some resistance in this. As we were talking about the wire wound resistor, this basically almost looks like it. So we're going to get some resistance from all these loops in here, which is going to be in series with the inductor. We're also going to get some parasitic capacitance, because if you look at an inductor, it's basically loops, and the current in here, in this loop, will cause some displacement currents in here, and that's a parasitic capacitance that we just are going to have to also include in here. So from a simple inductor, we get this fairly complex model, and using some circuit equations and circuit theories, obviously these in series, these in parallel, all this in parallel, we can basically draw a little bit simpler circuit, which we could go down here. So right here is just the more simplified version of the equivalent circuit. So from this, we get a fairly complex equation for the impedance. We'll just put that, okay, well I wrote that off. Well, should have gave myself a little bit more room, but we'll make do with what we got. That's Z equals J omega L plus the parasitic resistance, no, over 1 minus omega squared. That's because the capacitor is 1 over j omega L and the inductor is j omega L. That's where this minus sign comes from. L C parasitic plus j omega C parasitic and R parasitic. I know it's going to be hard to see down there, but this is basically the equation for the inductor to get its impedance at the non-ideal behavior point. So I rewrote down the formula for impedance so it could be seen better. And now it's about time we should see what this formula does as we go through the frequency range. So we're going to first begin by going low frequency. This formula is slightly complex, so we're going to just stick with the model. So at low frequencies, well, what should we expect, I guess? Well, you know that the inductance at low frequency, basically almost DC level, is just going to be a short. So it's just going to be basically a wire right there. I'll just redraw here. The resistor is not going to be affected by it. It's just going to act like a resistor. Now the capacitor. I know we haven't fully discussed capacitors yet, but capacitors at low frequencies basically just act like an open circuit, so it's just an open circuit. So from here we could see that the parasitic resistance is going to be dominant at low frequencies. So now let's talk about, I guess, medium frequencies, you know, above low but less than high frequency. So we'll put medium. Now let's just see what the inductor does at medium frequencies. Well, for one thing, we're going to for sure see that the inductor is just going to act like an inductor. The resistor, well, basically going to be just another inductor. And the capacitor, basically just an open circuit again. So we're going to see that it's just going to be basically an inductor. So inductance is dominant. Now let's go to high frequencies. So at high frequencies, the impedance formula for an inductor is j omega L. So as the frequency goes up to infinity, this is going to be infinitive impedance. So it's basically going to be an open circuit here. Resistor, well, we're not going to worry about that, but we can just put it there as the parasitic resistance is going to be there. Capacitors, the impedance formula for capacitors is 1 over j omega c. So as the frequency shoots off to infinity, the impedance of the capacitor is going to shoot off to 0, so basically being a short circuit. So basically here, this doesn't really matter. So we see that the capacitor dominates. Okay, so now we know what it does at low, medium, and high. Well, when does it change these states? Well, if we look at this model, we could basically see this inductor. This is just going to limit current, so we could just basically consider it a short for a high level thinking. So we see an inductor in parallel with the capacitor, and we discussed about this earlier. It's what's used to be a resonator, you know, a resonator circuit. So we know that omega equals 1 over square root of L. Just like the same as a resistor, something's going to happen here. So now we should go ahead and graph what the inductor looks like through the frequency band. We're going to first by defining where it resonates. The one formula, you know, omega equals 1 over square root of LC. So we're just going to draw that because I don't have an LCR meter, so I can't really depict what this is going to do. This is all theoretical right now, so we're going to put this as omega naught. And obviously, just so we can make sure we're on the same page, the y-axis is impedance, so in ohms, and the x-axis is frequency and in hertz. So, as we talked about earlier, at these low frequencies around here, you know the impedance is going to be low because the inductor is usually made out of copper, other stuff, which is highly conductive, so resistance is going to be low. And we described as the frequency gets a little bit higher, it starts acting like an inductor. Well, we know that the impedance of the inductor, equals j omega L, so we can see as the frequency keeps increasing, omega, which omega equals 2 pi f, you know that this is going to keep getting bigger and bigger and bigger and bigger. So we know from here, it's just going to go up, 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 till it hits this turning point at omega naught where the inductor resonates. And after that, what's it going to do? That's when we start seeing it go in high frequencies. And we found out that the capacitance effect dominates the inductor, so it begins acting like a capacitor. So the impedance of a capacitor equals 1 over j omega c. So as we see, as frequency keeps going up and up, this should just eventually go down to 0 because this is basically going to act like a short zero impedance. So it begins going down. And this is the graph of the inductor where we see that inductance up till it hits the resonance frequency, and it begins acting like a capacitor at frequencies above where it resonates. Hope you guys like the second edition of Technical Tuesdays. Next week we'll be finally diving into capacitors, so hopefully I can make some sense of all this stuff. Thank you so much.